Everyone. Today I'm excited to present our work on LLM resource allocation with deep reinforcement learning, a soft actor critic based approach with expert policy imitation. This project, developed in collaboration with Ayush Upadhyay, focuses on addressing the pressing challenges of efficiently allocating computational resources for large language model training. Training LLMs like GPT-2 and GPT-3 is expensive and resource intensive. Mismanagement can cost tens of thousands of dollars daily. Through this work, we aim to make LLM training more cost effective and sustainable while ensuring optimal resource utilization. LLM training is unique due to its high variability in resource usage during different phases, such as forward passes, backward passes, and optimization steps. This variability is compounded by the complexity of distributed training methods like data and model parallelism, making static or training schedule methods like first come, first serve or round robin inadequate. A significant challenge is balancing high GPU utilization with efficient task scheduling to avoid idle resources or bottlenecks. We also need to account for changing resource requirements throughout the training process. Addressing these challenges is crucial because even small inefficiencies in resource scheduling can lead to substantial cost overruns. Traditional schedulers such as first come, first serve, shortest job first, and round robin often fall short in LLM workloads. These methods ignore critical factors like the dynamic nature of resource needs, dependencies in distributed training, and the need to optimize for long-term performance. Recent advancements, such as deep reinforcement learning and cloud resource scheduling, have shown promise. However, these approaches often target general workloads, not the specific demands of LL training. Our work bridges this gap by training DLR methods to the nuances of LLM workloads. Our solution builds on the deep RM architecture, integrating soft actor critic, a reinforcement learning algorithm designed for continuous action spaces. We enchant SAC with expert policy imitation, which accelerates learning by guiding the model with tried and true heuristics like shortest job first scheduling. Key innovations include a state space representation specifically designed for LLM workloads, a reward function balancing resource utilization and training efficiency, and mechanisms to handle distributed training scenarios effectively. Our implementation ensures adaptability to dynamic changes while maintaining stability and efficiency. We modeled the resource allocation problem as a Markov decision process, MDP, where the state captures system metrics. The action defines resource allocation and the reward balances utilization, efficiency, and stability. Our state space includes historical utilization trends, current resource usage, and task queue details. The action space allows fine-grained controls over the GPU, CPU, and memory allocation, while the reward function penalizes overutilization and rewards balanced, efficient scheduling. Initially, we experimented with PPEO and DQing, but switched to SAC for its ability to handle continuous action spaces, faster convergence, and improved stability. Our implementation is composed of three main components: an environment simulator based on deep RM, modified for LLM-specific workloads, a SAC agent built into PyTorch that incorporates expert policy imitation to accelerate learning, a resource monitor that profiles system metrics and tracks training progress. We profiled GP2 training tasks to design and refine our state space, using tools like PyTorch, Profile, and GPUtil to gather detailed utilization data. By simulating synthetic workloads, we ensured our framework could handle diverse, realistic conditions. So for our results, SAC becomes performed just as good as baseline, but the performance degrades over time. And our baseline performance is a strong expert because of the best decision aggregation, as you can see in the graphs. And then our SAC plus the imitation learning actually significantly outperforms the SAC just alone by itself. To summarize, our contributions include a tailored state space representation and reward function for LLM workloads, the application of expert policy imitation to enhance learning efficiency, an enhanced SAC based architecture designed for continuous adaptive resource allocation, a robust profiling framework for evaluating LLM training workloads, open source code and protocols to facilitate future research and development. Our work not only advances resource scheduling for LLM training, but also sets the stage for broader applications in AI infrastructure management. Looking ahead, we plan to expand our framework to support even larger workloads such as GPT-3 and Palm models. We also are exploring the integration of additional scheduling objectives such as energy consumption and fairness. Finally, we aim to enhance our simulator to incorporate real-world scenarios such as network bottlenecks and hardware failures to make our approach even more robust and versatile. Thank you for watching. We believe our work demonstrates the transformative potential of reinforcement learning and optimizing AI infrastructure. We're happy to answer any questions, and then please check out our GitHub repository that is on our report. Thank you.